Well, hello and welcome YouTube. It's Mr. Robinson here with another brand new exciting video. All math-based, of course, and as always, it's an honor and privilege to be serving you today as this every day here in my virtual classroom. Step on inside, get some Family Guy. We got some Family Guy in the background. I hope I don't get a copyright claim from Fox. All right, we are going to be simplifying radical expressions, adding, subtracting, multiplying, and dividing them. So if you simplified radical expressions before, in general, just like a root 8 is 2 root 2 kind of thing, then perfect, you're in the right venue as we continue to simplify through different operations. Add, subtract, multiply, divide. I have 26 problems for us to do. We'll go calculator free, and we'll see how it goes. All right, number one, simplify. Square root of 45 plus square root of 45. Now you can treat these radicals, look, it's not square root of 90. We're not adding those like that. Square root of 90 is not the same thing as root 45 plus root 45, but instead just treat it like an x, almost like x plus x here would be 2x. Root 45 plus root 45 is indeed 2 root 45. Now there's one difference with something like this here though. X can't be simplified, root 45 can. See, the square root of 45, and this is one of those things where eventually I'm going to go a lot faster with this, but root 45 is root 9 times root 5, and the square root of 9 is 3, so 2 root 3 times 5 becomes 6 root 5, which ends up being our answer. Now, I simplified last. I could have simplified first, root 45 being 3 root 5, plus this root 45 being 3 root 5 also would have given us the 6 root 5 we're looking for. And, you know, maybe you saw this way and you liked this one more. Obviously, knowing this was already 3 root 5 maybe made this look faster, but maybe just doing this once made this look faster as well, depending on how you do it. I generally recommend you simplify first, though, and the reason is we hit a problem like number 2, root 24 minus root 54. This is like x minus y to me. They are not the same value. It doesn't become negative root 30 or something like that. They don't combine. So let's simplify them and see if maybe they can have the same radical, and then we'll simplify them from that. The square root of 24, this is where I'm going to start to go faster, is root 4 times root 6, which is 2 root 6. Root 54 is root 9 times root 6, which is 3 root 6. And now, since they're both root 6's here, it's like a 2x minus 3x to me now. This would combine to become negative 1x, negative 1 root 6, negative root 6, just like that. You can check these with the calculator. You can check and see if some calculators actually do give you this straight answer like that. Some of them will give you the decimal version of whatever that is, like close to negative 2.4-ish or something like that. You can see if that gives you the exact same value, and it should. So that's what simplifying does. It's equivalent, but a different version of it. And that's why simplifying radicals is a thing. Not just here, but also, that is among one of the reasons you can combine things that otherwise wouldn't have been able to combine. No matter whether you like the appearance of this more, it is simplified. All right, root 45, that's going to be our 3 root 5. Root 9 times root 5. Root 24 is 2 root 6. Root 45 once again. And, this is one thing where I already started simplifying. I might as well. Maybe it could have combined with this. Looks like it won't. 3 root 5 plus 3 root 5 is 6 root 5, which is what we'll get there. Minus 2 root 6 right here. These do not combine. Boo hiss. It happens. They don't combine. That's still simplified. That's your final answer there. And you can see where I'll kind of start to speed up as we go there. Root 9 times root 2 gives us 3 root 2 there. Plus a 1 root 2 here. Plus 25. So what I'm doing is I'm trying to find perfect square factors. The largest perfect square factor that I can. 25 happens to be it, as long as 50 is not a perfect square. 25 times 2 is 50. Root 25 is 5 times root 2 is yes. And then another 3 root 2 right here. All of these have root 2's. Woohoo! 3 plus 1 is 6 plus 5, or plus 4 is 4. Plus 5 is 9. Plus 3 is 12. So we're going to get 12 root 2 from that. Negative 3 root 8 plus 4 root 8. Now this seems easier than those ones, and for the most part it is. The difference is now with the factor in front of there. Just make sure as root 8 is 2 root 2, you are multiplying negative 3 by 2 root 2 like that. And then 4 is multiplying also by the same 2 root 2. And, yes, I could have done negative 3 plus 4. Honestly, this would have been faster. Negative 3 plus 4 is 1. This would have given us root 8 right off the bat. I'll show you these are both the same. And root 8 is 2 root 2. Let's see if we get the same answer here. Negative 3 times 2 is negative 6. And by the way, just these multiply. The irrational stays the same. And 4 times 2 is 8. Negative 6 plus 8 is 2. We get 2 root 2 there. So you can see, once again, maybe there's an added benefit to when adding and subtracting. If you do have like terms, and that's all you have, like terms with the same radicals, to just keep them the same and combine them. But if there are other ones within there that can simplify, and you want to check and see if it can combine with it, I would simplify first, or none can combine, like this one right here, simplify immediately. I would go straight to it. So negative 3 times root 32. Okay, let's do this fast this time. Root 16 times root 2 here is 4 root 2. Negative 3 times 4 root 2 is negative 12 root 2. Plus 128, 64 and 2. Root 64 is 8. 8 times 4 is 32. 32 root 2. 72, 36 times 2. Square root of 36 is 6. 6 times negative 3 is negative 18. So negative 18 root 2. All root 2's, all can combine. Negative 12 plus 32 is 20. Minus 18 is 2. Also 2 root 2 as an answer. Who knew that that and that were the exact same value? Well, I didn't until right now. All right, number 7 has cube roots here. So you're not extracting perfect squares anymore, but rather perfect cubes. Cubes such as 8, the cube root of 8 is 2. Cube root of 27 is 3. Cube root of 64 is 4. Cube root of 125 is 5. Numbers like that. I don't know if they get that big. It doesn't look like they do. This is the only cube root problem I believe on the sheet. So cube root of 54, let me write that out this time. That's cube root of 27 times cube root of 2. I picked 27 because it is indeed a perfect cube, which is 3 times the cube root of 2. Cube root of 6 cannot be simplified. No perfect cube factors inside there, so I'm going to leave that as a cube root of 6. And it looks like it can't combine with that there. And cube root of 48, I guess 8 times 6. So cube root of 8 is 2. Cube root of 8 is 2. And then cube root of 6 will remain as it is. So 2 times cube root of 6. 3 times cube root of 2. Oh, sorry, that doesn't combine with anything. Cube root of 6 plus 2 times cube root of 6 is 3 times cube root of 6. So we get 3 times cube root of 2 plus 3 times cube root of 6. And again, those cannot combine. We'll keep them as such, and we are done. Fourth roots. Okay, fourth power values are 2 to the 4th is 16. 3 to the 4th is 81. 4 to the 4th is 256. So we're not getting that large. We're not even getting to 81. The highest number is 80. So it looks like we're really looking for 16s if they exist. And if not, then I guess it probably can't simplify. So like that can't simplify. That's still negative 2 times the 4th root of 5. 64 is 16 times 4. So that would be the 4th root of 16 is 2. So 2 times the 4th root of 4. And don't think the 4th root of 4 can simplify. It's not 1. It's not 2 like a square root. It's just not a perfect fourth power. Perfect quartic. 2 times 4th root of 80. Okay. 4th root of 80. So 16 times 5. 4th root of 16 is 2. And 2 times that 2 is 4. 4 times, that's a 4. 4th root of 5 right there. You know, I'm kind of in between that, like, I want to go fast, and I'm kind of going fast. I really am. And some people saying you're going too fast. This is, you know, I get my students always telling me I talk too much. And listen, I do. I'm tailoring to the lowest common denominator. I want to make sure it makes sense and slow down when I can. Right now I am. You could write something down. Negative 2 times the 4th root of 4 plus 2 times the 4th root of 4 is bye-bye. And negative 2 times the 4th root of 5 plus 4 times the 4th root of 5 is 2. I think positive 2 times the 4th root of 5. And I'm trusting I'm getting these answers correct. I don't have anything in front of me telling me whether I am or not. So apologies if not. Just follow along. All right, that was adding and subtracting. Now we're going to start multiplying, which will, in time, involve adding and subtracting. Now, same thing as before. We could simplify radicals first and then multiply, or the other way around. I'm going to err to whatever side I feel is most necessary. 3 times 12 is very basic. That is 36. And yes, you do multiply within here. That's square root of 36, which is 6. So unlike adding and subtracting where you don't combine things that are not alike, here you do. I mean, that's what simplifying radicals was all about to begin with. The square root of 8 is root 4 times root 2. Well, hey, those multiply to become 8 as well, right? So same thing here. So look, that answer's 6. I didn't even have to simplify this, but I could have. I could have done root 3 times root 12 is root 4 times root 3, which is 2 root 3. And root 3, and I want to show this for a different reason. Root 3 times root 3 is 3, right? It's the square root of 9, which is 3. So that's 2 times 3, which does give you 6. So anytime you have a a square root of some value, it can totally be prime. If you have duplicates of them, root a times root a is totally A, bruh. There it is. It's A. There we are. Okay, so why did I start that second one? That looked a little harder than what I just did here, right? Well, do that here. The square root of 42 times the square root of 18. Figure that out. I'll wait. Figure that out, and then simplify it. So we have options here. My main thing is simplify what we can. Now, the square root of 42 contains no perfect square factors, so for the time being, I'm going to leave it. I'll leave it as square root of 42. I might do something with it in a sec. I'll show you what it is. Here's the thing. I haven't done the problem yet, so I can't tell you whether it's going to be beneficial to do it or not. Negative 7 is still as it is, but the square root of 18... Oh, let me change this. The square root of 18 is root 9 times root 2, so 3 root 2. 3 times negative 7 is negative 21, and this is times root 2 like that. Okay. I don't know why I put parentheses. That actually is probably worsening it, because the negative. All right, root 42 can multiply by root 2, and we will get root 84 out of that. So that becomes negative 21 root 84. But are we done? Well, no, because the square root of 84 can contain perfect square factors. In fact, 4 is one of those perfect square factors. I think it's the largest one. So root 84 is root 4 times root 21, and the square root of 4 is 2. So it becomes 2 root 21. Negative 21 gets to multiply by the 2 to become negative 42. And I get negative 42 times the square root of 21. 21 may not be a prime number, but it doesn't contain any perfect square factors in it. And that is as simplified as I can get. Was that the only way to do it? Heck no. One of the versions was going to be root 42 times root 18, get the massive number that it is, whatever it is, and then simplify that. I don't want to dare do that. The alternative would have been this, and where would have I gone from here? Let's... breaking this down into you could have chosen to not break this down as well, and I can show you 1/3 version of that. Then I'm going to start speeding up again. So if I have the root 2 times root 42, so we turn it to root 84, right? Here's the thing. Root 2 has no perfect square factors. Root 42 has no perfect square factors, but they share a common factor, apparently of 2. If I broke root 42 down into, 42 is 6 times 7. So it's 2 times 3 times 7. If I broke it down into root 2 times root 3 times root 7, then you would have seen a version of this problem that instead could have said, and here's the thing, negative 21 I'll put first. So negative 21 times root 2, and then let's put root 42 in there, times root 2, times root 3, times root 7. Remember what I said about the square root of a times the square root of a is a? Well, here's the square root of 2 times the square root of 2, and that's 2. That's 2. Negative 21 times 2 times 21, root 21 right there. And that would have given you this answer. Right, so there's another version of you can pair some things off. And that's how some students do their simplifying radicals. They'll go into a prime factorization of that thing. And that's something I could have done with 18 as well. Right, 18 could have been root 3 times root 3 times root 2. And we would have paired off any things right here. Root 2 would have paired off with root 2 to become 2. Root 3 would have paired off to root 3 to become 3. 2 times 3 is 6, and 6 would have multiplied with negative 7 to get negative 42. And then root 3 times root 7 would have been root 21. It's a lot that I'm saying there. There's more than one way to do this. I personally prefer this one for myself because this number wasn't that big. If it was bigger, I probably would have broken it down to its primes to find it. And listen, it's not about being big. It's about finding perfect square factors. And if the number's weird for me, like listen, 1,000's big, but I know that it can divide by 100. So it's about if the number is too weird for me to find a perfect square factor. And if I can't easily, I'm going to maybe break it down to its primes. I'm going to try not do too many ways here on out. I'm exploring different options for you to consider. Let's continue multiplying, only now we have a monomial times a binomial, which does mean distribution. Now there's nothing I can simplify right now. Maybe I can in a bit. Root 15 times 5 is indeed 5 root 15. And root 15 times root 5 would be the square root of 75, like that. Now, you would be done if nothing could simplify, but you just multiplied root 15 times root 5. This has a perfect square factor of 25 in it. Root 25 times root 3 is 5 root 3. So this becomes 5 root 15 plus 5 root 3. And if anything could have combined here, I would have. Nothing can, so I won't. But once again, I did root 15 times root 5. 15 is also 3 times 5. Root 3 times root 5 times root 5, check that out. That becomes 5 root 3. when that there is that. So again, more than one way to do it. If you're hard pressed to come up with how to simplify that, break it down to primes. It doesn't have to be primes, just duplicates of square roots right there. Merge them together, make it become rational, see what you get out of it. All right, number 12, same thing as before. 10 times negative root 3 would be negative root 30. No perfect square factors inside. It can't simplify. Root 10 times root 2 is root 20. That can simplify to 2 root 5. So this becomes negative root 30 plus 2 root 5. I'm done. Again, nothing can combine there. And I move on. All right, the next two I'm going to be able to FOIL. I'm going to be able to distribute this where first outside, inside, last. Well, this one I get to. And that will give me 1 times negative 2, which is negative 2. 1 times root 5, which is root 5. I guess we kept this small. Root 5 times negative 2 is negative 2 root 5. And root 5 times root 5, we talked about that kind of thing. That's 5. So some rational numbers come out from it, and I can do negative 2 plus 5, which is 3. And root 5 minus 2 root 5 is negative 1 root 5. So 3 minus root 5. Done. So that's what we get to do with that foiling aspect there. This one right here, when you square, remember, that does not mean you just square that and you call it a day. You have two options. You may either distribute this as that and just FOIL the whole thing out. I'll let you play with that if you'd like to. Let me show you the alternative of it, of course. When you square a binomial, that becomes squaring the first term, squaring the last term, but also doubling the product of the two inner terms, and you add those all together. So this to me would become, normally I do this mentally, but I want to write this out. I would square root 2, I would double root 2 times root 5, and I will square root 5 like that. Root 2 squared is 2. Root 5 squared is 5. Root 2 times root 5 is root 10, so this becomes 2 root 10 like that. This is normally what I'd write, just boom, that. And then 2 plus 5 is 7. So we get 7 plus 2 root 10 like that. See if you get that by doing it the other way, expanding root 2, that thing like that. That's what we get. All right, next page here, and we are more than halfway done, and I'm only 17 minutes in. That's cool. Some of the other problems down here are going to take a little bit longer, though. All right, let's go ahead and FOIL again, as we can. Root 2 times root 2 becomes 2. Root 2 times negative 3 is negative 3 root 2. 4 times root 2 becomes 4 root 2. And 4 times negative 3 becomes negative 12. Not really different from that problem before. 2 minus 12 is negative 10. Negative 3 plus 4 is 1. So root 10 plus, negative 10 plus root 2. I wanted some to simplify and do some other things. It looks like that's not really showing up. In fact, those problems aren't really, that's nowhere near special compared to anything else. 2 root 2 times root 2. So here's the thing. Root 2 times root 2 is 2. Times that 2 is 4. So that one's 4. This is just good old-fashioned 2 root 2 biz. And that's minus 2 root 2, interestingly enough. Those looks like those will cancel. And negative 2 plus 1 is negative, times 1 is negative 2. 2 root 2 minus 2 root 2 is 0. 4 minus 2 is 2. All done there. So hopefully that's making sense as far as multiplication. You still combine things. Nothing's been simplifying. The numbers have stayed small. I think that's just how I chose them. No simplifying. But be prepared for something that could. All right, this. Yes, I could FOIL. But I don't know if you recognize here, it's a plus b times a minus b scenario. This is a difference of two squares. And this is important. It's one thing for me to say, hey, go and try FOIL. No. I want you guys to see this for what it is, because we are going to use this when we talk about conjugates on some problems down below. The last 4 problems. We're going to have to use what's called conjugation. And I want you to recognize what this is right now. This is a difference of two squares. This will become a squared minus b squared, where root 3, we're going to be doing root 3 squared minus 4 squared. I have no reason to use parentheses other than just to do it. Root 3 squared is 3, but 4 squared is 16, right? So 3 minus 16 is negative 13. I'm done. I'm done. You're squaring the first term, you're squaring the last term, and you're subtracting the result in differences of two squares. That's what happens. This next one right here is the exact same thing, difference of two squares. 5 squared is 25. Now you got to be careful on this one. Let me write this out. 2 root 3 squared. I need parentheses this time. This is 2 root 3 times 2 root 3. This is 2 squared, which is 4. Root 3 squared, which is 3. This is 12. It's not 6. It's not, other things that you might accidentally square and do whatever. That is 12. So 5 squared minus 2 root 3 squared. Okay? And that's 13. Negative 13, positive 13. I don't know if we're lucky or not right here. They cancel each other out. We're all good. We're all good. All right, that's some of the multiplying things. Now we're going into dividing. And listen, the first one we actually could probably do something with regard to dividing. But for the most part, we're going to tend to not actually divide things. It's division. But we're actually going to do more so. We're simplifying. That's actually the goal. It's a division problem that we simplify. And generally what's going to happen, unless you could reduce a fraction, is we're just going to try and make sure that our denominator is a rational value. Which means we're going to have to do something called rationalizing the denominator. I've had videos on it. We've done it before. But we can simplify this root 80, and that's something I always recommend, of course, right? The square root of 80 is the square root of 16 times square root of 5, so it's 4 root 5. So let's turn this instead. I got a root 5 on top, and I have 4 times 5, which is 20, root 5. So I have root 5 on top and bottom. That I'll actually be able to divide, reduce the fraction. Root 5 over root 5 is 1, so I'm left with 1 over 20. And I mean, hey, that's the answer. Alternatively, what I could have done here, it's a little interesting, as we can multiply two radicals together, like if I had root 5 times root 80, that would have been root 400. I could divide them as well. I could treat it like this. This could have been, how would I write this with the 5 there? I guess 1 over 5 times root 5 over 80. And you don't have to write it that way, but I want to express that I could have divided these. 5 over 80 can reduce to, I guess, 1 over 16, right? So this could have been root 1 over 5 times root 16. The square root of 1 is 1, square root of 16 is 4. And once again, we get 1/20. I probably wouldn't go that way. That doesn't really help contribute to the fact that if this wasn't a perfect square, I'd have to rationalize it. I'd rather simplify if I could. All right, number 20. 5 divided by root 2. Again, nothing you can really do. I'm not going to actually divide anything there. It's good. But I'm not done because we have an irrational denominator. I must rationalize the denominator. Multiply top and bottom by the square root of 2. That's what rationalizes it there. And that gets us 5 root 2 on top and 2 on bottom. Whether or not that looks better to you, it is simplified. We have a whole number denominator. That's kind of the overall appearance of what we need for a problem like that. Number 21 is going to be the exact same. First, see if anything can simplify and combine on top. It looks like you can't. But the bottom is a square root of 2. We're going to have to multiply top and bottom by root 2, which gives us a 2 on bottom. But the top gives us root 2 multiplying by that quantity. You got to distribute root 2 into both of those. Root 2 times root 5 is root 10, which cannot be simplified. Root 2 times 4 root 2 would become 4 root 4, or 4 times 2, right? Which is 8. I don't know why that took me a second. And then I'm done. Okay, I'm done. If this could reduce, we would have, right? If I could combine up top, I would have. If this could reduce, I would have. And you're looking at these and you're saying, hey, Mr. Robinson, I thought you could divide these by 2. Can I make this, can I turn this into 4 over 1? Can I divide that by 2 and turn to root 5? No, because this is an irrational value right here. Look, if this was 10 root 10, yeah, this would be 5, this would be 4, and this would be 1. But this is a root 10 right here. That is different. That means this is a 1 right here. If it can't divide by 2, you leave it. You leave it. And if I see an answer key, they might put that first. That's the extent to which you'll go. Kind of looks like quadratic formula answers that way, right? Only without the plus or minus. We're done. We're done. That's it. All right, 4 plus root 5 divided by 3 root 10. Now, in this problem here, once again, nothing to simplify. We're all good on that front. We will rationalize the denominator. But do I multiply by 3 root 10 over 3 root 10? You could. This will end up leaving you with something where you do have to reduce the fraction, though, because you just introduced a 3 on top and 3 on bottom that honestly were not needed. Rationalizing the denominator doesn't mean multiply by the bottom. It means multiply by the irrational components. Multiply with things from the irrational components that can rationalize it. I just need to multiply by root 10. I just need to multiply by root 10. See, the 3 is rational. The root 10 is not. When I multiply 3 root 10 by root 10 times root 10 is 10. That's what gets me a rational denominator. I get 3 times 10, which gives me 30. I'm good down there now. I don't need the extra 3 on top of it that makes these numbers bigger than they need to be, and then I need to reduce. That doesn't mean I don't need to reduce ultimately. We're going to see what's going to happen here. I don't know. But I don't need to reduce as much anymore. All right, 4 times root 10 is 4 root 10. I cannot simplify that in particular. Root 10 times root 5 is root 50, which I think we saw before is 5 root 2. So 5 root 2 like that, over 30. Nothing can simplify, nothing can combine, and nothing can reduce. If this 5 was a 6, yep, I could divide all those by 2, but it's a 5, and because that they can't all divide by the same thing, it's close to something that could reduce. I wish it did for the sake of argument, but it can't. I am done. Hopefully this is making sense as far as rationalizing. All right, the last 4 problems right here. This is where conjugation comes into play. What's a conjugate? I don't know if you remember this. When you multiply, I've done this in more recent, couple months ago, recent videos with imaginary values. If I had 5, I don't know why. Okay, if I had 2 plus 5i, its conjugate would be 2 minus 5i. Because what happens in difference of two squares form, that would be 2 squared minus 5i squared. By the way, this has nothing to do with imaginaries, but it has to do with conjugates. Which would be 4 minus 25i squared, and I squared is negative 1. That would become 4 plus 25, which is 29. I just turned, well, not turned this into, but these were 2 complex numbers with imaginary components, and when I multiply them out, it became real. It canceled out that which had imaginary portions in it, because when you square an imaginary, it becomes real. When you have the linear, the inside terms, they cancel out. This is going to be the same thing here. And we just talked about differences of 2 squares and things like that and what happened. And you actually saw it. We saw it in this problem right here. Prove me wrong. Number 17, I have irrational components. What happened when I multiplied a difference of 2 squares right here? Rational. Right here, irrational components. What happened? Rational. When you square an irrational number, a square root, it becomes rational. When you have a difference of 2 squares, the inner terms cancel. So there are no radicals left. So right here, I'm going to multiply. I have to rationalize the denominator. It's irrational. I have to multiply top and bottom by the same thing on top and bottom. And I'm going to choose to multiply by this guy's conjugate. Its conjugate is root 5 minus root 3. If I have root 5 plus root 3 right here, I want root 5 minus root 3 here. What will this do at the bottom? This is an a squared minus b squared approach. This is why I asked that you followed along with the last one, because I'm going to go whip fast on these after I do a couple. You're going to see me go a lot faster. But the bottom is a squared minus b squared. That's what it is, and it's rational. And that's what we're getting out of it. Now the top, maybe not so lucky, right? This looks like it's an irrational answer. Root 5 times root 5 is actually 25. It's 5. Root 25, which is 5. That's good. But root 5 times negative root 3 is negative root 15, which cannot simplify. So the top will be what it is. The bottom is 5 minus 3, which is 2. So I'm going to get 5 minus the square root of 15 divided by 2, which again cannot reduce further. We'll be done with that. But we've taken what was here and simplified simply by rationalizing the denominator. That was the goal. And to me, it looks cleaner argumentatively. It won't always, but this time it is. There's that. All right, number 24. You know, again, I can't just multiply by root 2 over root 2. That won't, it might take care of this term, but not that one. Suddenly that would be 4 root 2. 2 terms, binomial, I need to multiply by its conjugate in order to clear out the whole root 2 ordeal. And you got to go straight into, this is 4 plus 5 root 2. I got to multiply by 4 minus 5 root 2. The thing that gives me a difference of 2 squares there. And 4 minus 5 root 2 there. I don't think I'll generally use parentheses anymore. Hopefully you'll be accepting of the fact of what distributes here. All right, on the bottom, we have a squared, 4 times 4, which is 16, minus b squared, 5 root 2 squared. 5 squared is 25. Root 2 squared is 2. 25 times 2 is 50. So that's my denominator right there. That's my denominator, 16 minus 50, which of course I'll clean up momentarily. We got to distribute 3 root 2 into 4 and 3 root 2 into negative 5 root 2. 3 root 2 times 4 is 12 root 2. 3 root 2 times negative 5 root 2 is negative 15 times 2, which is negative 30. Oh, good. I think we can reduce this one in a second. So the top is still 12 root 2 minus 30. The bottom is negative, and there's something else I'm going to do here in a second. The bottom is negative, sorry, blank, drew a blank, 34, negative 34. All right, couple things I'm going to do with this. First off, everything here can divide by 2, okay? So I'm going to Not the 2, the rational numbers. So this will be 6, this will be negative 15, and this will be negative 17. So this will become 6 root 2 minus 15 over negative 17. Second thing, and this will be a picky thing on my end. Well, not really. This would, an answer key wouldn't show this. I've mentioned to my students in the past, and probably to you guys before, shouldn't have negative leading terms in a denominator. And when it's the only term, it definitely shouldn't be like that. So I got some options. I could make the fraction negative. But I don't think that still satisfies our entire ordeal of what's going on here. Why don't we just take that, and why don't we just make the top negative, which means apply it to the numerator, which means distribute into there. If I were a betting man to see an answer key, and I can't guarantee this, but if I were a betting man, I would bet that they distributed it into the negative, they made the 15 positive, therefore, and they even wrote it first. I bet it's 15 minus 6 root 2 all over 17. I don't know where to find a key. Go ahead and photomath it. See if you get that answer. I don't know. But that's my bet. That's what I'm going to go with. Now, whether or not they do that, definitely get the negative out of the denominator and definitely reduce the fraction. But that's my go-to answer. But the main highlight of this, of course, is rationalize the denominator. And, of course, yes, reduce the fraction after. Simplify what you can. It's too bad these aren't simplifying more things. That's probably on me. I made the problems. I randomly generated them. But I wish I was doing more. Oh, and that's a root 20. And now let's simplify it. Make sure you keep doing it. I got to make sure to create more problems like that. All right, rationalize the denominator here. This is where I'm not going to write parentheses. 2 minus root 5. I'm going to show the work. All right, let's see if we can do this in our head this time. A squared minus b squared. That is 4 minus 5. That's negative 1. Ooh, another negative denominator. But it is negative 1. That's really easy to work with. This top has to FOIL, though, right? We got to do, maybe I will put parentheses on the top here. Got to do 8. And there's no faster way that I do this. I'll just do this. 8 minus 4 root 5 plus 2 root 5 is negative 2 root 5. And then minus 5, right? Root 5 times negative root 5. So minus 5. And that's going to be 8 minus 5 is 3 minus 2 root 5. And this is all divided by negative 1 still. Now, when you divide by negative 1, guys, you're just switching signs. This will become negative 3 plus 2, root 5, just like that. So it's just like multiplying by negative 1, right? Put the negative here, distribute the negative into, divide by 1. Values don't change. Okay, I got one more problem for you, and then we are finished. So let's take a look. Conjugate. What is it? It's going to be 2 root 3 plus 4 on top and bottom. So on bottom, 2 root 3 squared is 4 squared times, 2 squared is 4 times root 3 squared is 3. 4 times 3 is 12. So a squared minus b squared, that's 16. Another negative. It looks like that's just showing up a couple times. I think it's a value that we have this. Let's FOIL. Try this out. 10 root 3 plus, I kind of need parentheses, plus 20 plus root 3 times root 3 is 3 times 2 is 6 plus 6. It's weird when the inside is actually the rational numbers. I generally don't see this. Plus 4 root 3. Okay, I'm going to put the rationals first. So 26 plus 14 root 3, all divided by 12 minus 16 is negative 4. You can bet we're going to be reducing things. You can bet I'm going to take care of that negative in the denominator as well for, sake. Divide everything by 2 again, it looks like. So that's 13, and that's 7, and that's negative 2 now. Let's take care of that negative. I'm going to bring it up. Sorry for the squirmy work. I'm going to bring it up and distribute into that. So what does that become? On top, negative 13 minus 7 root 3 all over 2. I'm not opposed to having the negative in front of the fraction if you absolutely so need it to be. I can see that being an answer there. I would expect that probably. You're not going to see a negative 2 in the denominator. It's taken care of somewhere else in the fraction. That's a guarantee. All right, hey, and that's it right there. We simplified radicals a lot more in the beginning, it looks like. I do wish, I think the numbers would get too big if we were doing it the other way, or at least I feared that, so I set it up with smaller numbers. I think it was more about conjugation anyway. You got to play with fraction reduction. But that ought to do it, guys. This is Mr. Robinson. Thank you so much for watching, and take care. I will see you in the next one.